Hello students. Today we are going to see the topic organic reactions. First of all, we will start with Wittig reaction. This reaction is named after the German scientist George Wittig. It is an important and useful method for synthesis of alkenes. Now let us see the definition. It is the reaction between a phosphorane or phosphonium halide with an aldehyde or ketone to give phosphine oxide and an alkene. In the given equation, you can see the phosphorane. It is reacting with the ketone to give phosphine oxide and an alkene. The reaction takes place easily under mild conditions. Valuable feature is that double bond can be predicted. High yields of di and tri-substituted alkenes are obtained, but low yields of tetra-substituted alkenes due to steric effects. The rate can be increased by adding HMPA or to catalytic amount of crown ether to the reaction window. Then let us see some other examples of this Wittig reaction. The above two are the two examples. This phosphorane reacts with a ketone to form an alkene, and another phosphorane reacts with an ester to form an alkene. Now let us see the structure of phosphoranes. They are resonance stabilized structures. There is overlap between the carbon p orbital and d orbital of phosphorus. The bond is called d pi p pi bond. You can see here, this is the phosphorine form of the reactant, and this is the halide. The negative charge on the carbon atom of the halide, this one, it is responsible for the nucleophilic attack of the carbonyl carbon, resulting in a formation of butane. It is converted into a four-membered cyclic transition state. The driving force is formation of strong phosphorus-oxygen bond. Electron withdrawing groups on the carbonyl carbon increase the rate of the reaction. Electron donating groups on R1 and R2 increase the rate of the reaction. The more electrophilic the carbon, the more readily the reaction takes place. Therefore, reaction with aldehydes takes place more readily when compared to ketones. In the following example, you can see here, this is a phosphorane. It reacts with two molecules, crotonaldehyde in the presence of benzene, and upon reflux, you can see the following alkene. And similarly, the same phosphorane reacts with cyclohexanone in the presence of benzene, and upon refluxing, it is giving this product alkene. Let us see the applications. This Wittig reaction is used for formation of exocyclic methylene groups and synthesis of large rings containing 15 to 16 carbon atoms. So in the first application, you can see cyclohexanone reacting to form methylene cyclohexane. This double bond is present out of the ring, so it is called as a exomethylene group. Synthesis of large rings containing 15 to 16 carbon atoms. The next reaction we can see is Stork-enamine reaction. It is introduced by a scientist called Stork, and it is widely used in synthesis. This reaction provides an alternative method for selective alkylation and acylation of aldehydes and ketones. Now let us see the definition of Stork-enamine reaction. Enamines on treatment with alkyl halides and acyl halides and subsequent hydrolysis gives alpha alkylated and alpha acylated ketones and aldehydes. This is known as the Stork-enamine reaction. Now this is the enamine. Enamine on treatment with alkyl halide, you will get alpha alkylated ketone. Now, enamines are prepared from ketones. The end product is alkylation of the same ketone from which enamine is derived. Now, enamines are alpha beta unsaturated amines. How are they prepared? They are prepared by reaction of aldehyde or ketone with secondary amine in the presence of dehydrating agent like K2CO3 or by heating in benzene solution in the presence of catalytic amount of toluene parasulfonic acid with azeotropic removal of water. All the steps in the enamine reaction are reversible and enamines are readily hydrolyzed by water to reform carbonyl compounds. So all reactions are carried out under anhydrous conditions. Primary amines give imines and elimination predominates with tertiary amines. The aldehyde and ketone should have an alpha hydrogen. When you look at the reactivity, the usefulness of enamines is due to the development of some negative charge on beta carbon, and it acts as a nucleophile in alkylation and acylation reaction. For example, you can see in this reaction, in the following, this is enamine is resonance stabilized. Here, nitrogen is having lone pair of electrons. When this pair of electrons is shared by nitrogen, carbon acquires negative charge. So this acts as a nucleophile in alkylation and acylation reaction. Now let us see alkylation. Enamine alkylation has a number of advantages over direct base catalyzed alkylation of aldehydes and ketones. This is because no acid or base catalyst is required. This results in preventing wasteful self-condensation reactions of carbonyl compounds. Enamines on reaction with alkyl halides give C-alkylated and N-alkylated products reversibly. C-alkylated products on hydrolysis gives alkylated ketone, and L-alkylated products are usually water-soluble and unaffected by hydrolysis. Now, this is the example. Here we can see the ene and the enamine on refluxing with methyl iodide benzene. You can see C-alkylation here and also N-alkylation. In aliphatic compounds, N-alkylation is predominant, and in aromatic compounds, C-alkylation is predominant. In case of alkylation of unsymmetrical ketone, the double bond is directed towards the less substituted carbon. In the more substituted enamine, there is decreased interaction between the nitrogen lone pair and pi system of the double bond. This is because of steric interference between alpha substituent CH3 and the methylene alpha methylene of amine. So this is the example. This is a ketone and the secondary amine. In the presence of paratoluene, sulfonic acid, and benzene, you will get a mixture of 85% of one compound and 15% of another compound. Alkylation of enamines with electrophilic olefins like alpha beta unsaturated ketones, esters, or nitriles give a high yield of monoalkylated carbonyl compounds. Now, these are the examples, electrophilic compounds, and these are the products which are obtained, we can see in the slide. Now, that's all about alkylation. And next thing is acylation. Enamines are readily acylated with acid chlorides as anhydrides to give an intermediate, which on hydrolysis gives 1,3-diketones or beta-diketones. Good yields of C-alkylated products are obtained. Triethylamine is used to neutralize the HCl formed in the reaction. So this is the acylating reagent and this is the enamine. And this is the product which is obtained, which on final hydrolysis will give a 1,3-diketones or beta-diketones. The next reaction is the Shapiro reaction. let us see the definition of this. Base catalyzed decomposition of aryl sulfonyl hydrogens of ketones or aldehydes to give vinyl lithium, leading to the formation of an olefin called Shapiro reaction. Now let us see the mechanism. This is the ketone and this is aryl sulfonyl hydrazone, and in that you will get the product which is nothing but an olefin. The mechanism involves deprotonation with a very strong base, usually butyl lithium or LDA, that is lithium diisopropylamide, to form hydroxoazoenolate. It eliminates the tosyl group to give an unstable anion. Loss of nitrogen is extremely favorable, resulting in vinyl lithium. The key step is elimination of tosyl group, and the rate of elimination is improved by using aryl hydrozones with bulky isopropyl groups or 246 positions of the aromatic ring. Now let us go back to the mechanism. First thing you can see here is both of them react to form this type of compound. In the presence of RLI base, deprotonation will take place. Next, loss of tosyl group in a slow step and rate determining step. And in the next step, loss of nitrogen. This one is a hydrazone as a enolate. And this is formed as an intermediate. Now, evidence for this mechanism. Two equivalents of RLI are required. The hydrogen in the product comes from water, not from the adjacent carbon atom shown by deuterium labeling. All the intermediates have been trapped. In the case of unsymmetrical acyclic ketone, both regio and stereochemistry are to be considered. The CN bond in the starting hydrazone is responsible for regiospecificity. The proton syn to the tosyl group is removed due to the fact that rearrangement allows chelation with lithium ions. The reaction also takes place with other bases. Example, lithium hydride, sodium in ethylene glycol, NaH, NaH2, or small amounts of lithium. The next reaction is Mannich reaction. Let us see the definition of Mannich reaction. Formaldehyde condenses with ammonia or primary amine or secondary amine and with a compound containing active hydrogen to give beta-aminocarbonyl compound. An acidic or basic medium is required. The reaction can be formally considered as addition of amine to give NH2CH2OH followed by nucleophilic substitution. This is formaldehyde. It condenses with ammonia or primary or secondary amine and with a compound containing active hydrogen to give beta-aminocarbonyl compound. The product is referred to as Mannich base. Instead of ammonia, if the reaction is carried out with the salts of primary or secondary amines or amides, the product is substituted on nitrogen with R1, R2 and RC. Aryl amines do not normally give the reaction. So these are the two process, the base catalyzed reaction and an acid catalyzed reaction. In acid catalyzed mechanism, the active hydrogen compound reacts as enol. There is kinetic evidence for the intermediacy of the iminium ion. When an unsymmetrical ketone is used as an active hydrogen compound, two products are obtained. It is clear that Mannich base contains two methylene groups, one coming from formaldehyde and the other coming from ketone. This has been demonstrated by C14 labeling experiments that showed no skeletal rearrangements. The use of ammonia and primary amine is undesirable in Mannich reaction because the first formed Mannich base will still carry hydrogens or nitrogen and will thus continue the reaction. Now let us see some of the applications of Mannich reaction. It is an important biosynthetic route to natural products, mainly alkaloids. Example, Robinson synthesis of tropinol. It involves double Mannich condensation with succinaldehyde. The synthetic importance is that Mannich base is converted into various products of interest.